Hello, I am Abhinav Chandrakar and I am the TA for this course, Strength of Materials, which is conducted by Professor K. Ramesh of IIT Madras. I am the TA along with the other TA, who is Ms. Archita Gogoi. In today's lecture, we'll cover the doubts and problems associated with contents of week 9. This is majorly on bending of beams. So we'll look at um, what are the stresses which develop in bending and how we can mathematically write them down, as well as form relationships between the stresses and strains for different kinds of loading. So before we start, I'll also like to share that I'll be covering bending 4 and bending 5 lectures. So there were 3 lectures this week. I'll be covering 2 of them. Bending 6 will be covered by Archita in the problem solving session which she conducts. So as usual, we'll first start with a bit of summarization of the contents of week nine's video lectures. Um, Once that is done, I'll take some doubts if there are any, and then we'll move to some questions which are associated with week 9 content, which we'll try to answer. Yeah. In the previous week also, we had seen bending of beams. There we had understood what is the nature of the stresses which develop on pure bending. After that, we looked at addition of shear in bending because that is more realistic. That is what practically always occurs. And how will be the stress distribution and the strain relationship when you have both bending and shear. Okay, I'll start my camera. Mm. Yes. So, and after that, we had solved some problems where we looked at the stress distribution for different kinds of loadings and also the effect of the cross section on the stresses and strains which are developed. So since we have a moment of inertia term also coming in the expression of uh, bending stress, so the cross section area and the shape of the cross section also affects the stresses which are developed. In this week that was continued and some more advanced concepts were covered. I'll quickly summarize through them in the through the notes which I have written. So previously we had seen how shear presence of shear, which is natural when you have any kind of bending, for example cantilever bending or 3-point bending, how that affects the bending moment, because the bending moment will affect the axial stresses which are developed. So we'll have to see the contribution of shear stresses to the bending moment. And we had understood through what's are called engineering analysis, which is a more approximate analysis of how the stress and strains develop in the material and how we can represent it. But Sir had mentioned towards the end that if you have, instead of a bulk beam, if you have different layers of beam stacked one over the other, and then you try to load it, give a bending load, what will happen? So that was covered in this week in the first lecture. There we could see that in case of a layered beam, that is, you have different number of layers all stacked one over the other. The deflection when the same amount of loading is applied is much more compared to a homogeneous bulk beam. If you do some pinning of the layered beams, the deflection is somewhat lesser than that of the layered beams. And the reason we have this much of deflection is because slipping occurs in between the layers. We also saw it in the video of the loading which sir had shown. And when we try to look at the forces acting between the layers, it was seen that there is a shear force which is acting between the layers. And mm, yeah, it was mathematically quantified by looking at force equilibrium for that shear force. Here I have written down the final expression for the delta Fyx force acting in the on the y plane in the x direction, which is basically the shear force on a layer. And it can be related with the bending moment value Izz and the integral yda, which is the first moment of area. And finally, when we do some substitutions, we call df by dx as q, which is the shear flow. So how sir linked it with the flow of material, how as you change x the force is changing. And you can also write tau as q by b. So q is the this shear flow here, and b is the width of the beam, and this will be equal to just a minute. Okay. Sorry, I could not write on it. Anyways, so I'll just magnify the concerned area. So finally, we got this expression tau equal to q by b, which can also be written as v into capital Q. V is the shear force, which is acting at that point. Uh, Due to the loading. Q is your this first moment of area and divided by b into Izz. I is the moment of inertia, second moment of area. Mm. So by this we see that in cantilevers we also have a shear stress tau yx, which is on y plane in the x direction, y plane in the x direction. And this stress will be maximum on the neutral plane. So before also sir had told that the shear stress distribution will be such that at the surfaces it will be 0 due to free surfaces, and at the middle it will be the highest. And through this relationship, actually it's not written here exactly what is the relationship, but it's a parabolic relationship. So tau is parabolically or tau is proportional to the square of the y value. So as you go from neutral surface towards the neutral surface or neutral plane towards the top or bottom surface, the value of the shear stress will reduce in a parabolic manner from highest to 0, and the highest value will be Vh square by 8 IZZ, which is 3 by 4 into P by BH. So at the neutral plane, we know it's defined in such a way that the axial strain and on neutral plane is 0. So both axial strain, axial stress are 0. But the shear stress will be highest on neutral plane. So that you have to understand. And we know that we have all throughout made the assumption of slender beams. So L by H is more than 10. And if we try to take the ratio of the shear stress and the axial stress, it comes out to be H by 2L. And so from this, what we can understand is that axial stresses are normally much more than the shear stresses for slender beams, and therefore, in most scenarios, axial stresses are more important. So there are certain scenarios which Sir tells about where you have concentrated loads occurring, such as in 3-point bending test, and near those concentrated loads, shear stresses can play a big role. They can influence the stress contours which are developed. Hmm. Hmm. Also, till now we also considered I-beam, about which I talked previously, and I-beams are especially useful in railway tracks because the it is such that the material which is near the neutral plane uh, has been removed out, but at the top and the bottom of the I-beam, which are farther from the neutral plane, you have more material. So even though the volume of it is low, that is the cost of that material will be low, the moment of inertia is high, because of which it will be rigid to bending, and that can be helpful to prolong the life of your railway track for a particular volume of material that you're using. Those kinds of sections are called open sections. And if you have something like a rectangular cross section, you call it a closed section. So till now, all this that we saw, especially the shear stress related observations, they were for closed sections. So this will also apply to open section, but in open section there will be another kind of shear stress which will develop. So till now we were looking at shear stress between the layers, occurring between the layers between top and bottom. But if you have a open section, So depending on how the section is, I'll try to just write it down. Yeah. I'll just make a rough. So what I was talking about was, till now we looked at more symmetric sections, like maybe this kind of rectangular cross section, or a I beam which has a plane of symmetry, two planes of symmetry actually. But if you have something of this form, then in this case, what will happen if you make a vertical cross section, for example here, then you might have an element like this, or let me, mm, it's difficult to draw actually. But if you do a vertical cross section of this, make a vertical cut, and then try to, just like we had two different layers, horizontal, stacked one over the other. If you have them stacked vertically side by side, and you look at what will happen for the closed one, you will see that it will still be the same when loaded. The cutting vertically will not lead to any change in the stresses. But if you look at the open cross section and do this activity, what will happen is that one layer will try to shear past the other. Like there will be some movement occurring between those two. And that happens because shear force develops to counter the, to maintain equilibrium, or to, because here you do not have equilibrium maintained actually, that is why you have a shear force developing, a net shear force, and that is acting on this cross section. To see exactly how it is happening and why it is happening, you'll have to see Sir's video lectures. There he has explained it through very nice figures. Here I am just telling you, and that direction will be, just to clarify a bit more, if you have x here as per Sir's notation, y here, and z here, so that direction will be tau. So you will have one in the, hmm, okay, and beam is like this. beam is like this. So you'll have one shear in the x direction on the z plane, so tau zx, and similarly this will be same as tau xz. So on the z plane, x plane on the z direction. So these both will occur for this kind of a cross section. And sir has told what will be the values for this based on force equilibrium. And it turns out to be qzx by T1 in I beams. Also, it will also be for the, here I told, I think I said that it will be for this one, but it will also occur for the two plane of symmetry I beam also. This is half I beam. So this will occur for both of them. At the top surface, there will be some shear forces acting in the x in the on the z plane in the x direction, and their value will be given by minus vq divided by t1, the thickness, into izz. So at the flanges, which are the edges, for example in the I beam, the top portion, tau xz will be high and tau yx will be quite small. So the distribution is something like this. For this, if you want to look at tau xy, it will be, let's say for an I beam, to keep it more as per what sir had shown. So it will be slightly like this, parabolic, and this is for I beam. So the reason we have much lower, this is the x direction. Sorry, this is the tau value, and this is the y direction. Along y direction, how the value of tau xy is changing. We see that at the top it is very less near the flange area, and this is because the area of this is very high. So due to this, if we look at the formula, it's like this: vq by b into izz. So moment of inertia is very high, so tau will be low, and you will have a very small value. Both still show parabolic nature. So both of these are parabolic. But in the other portion, because the area is smaller and IZZ value is smaller, we'll have much higher tau values. So this is how tau xy will vary for open sections. Mhm. Also, all of this was from engineering analysis, which gives you a more approximate and quicker solution. but you can also get a more accurate solution by doing theory of elasticity analysis, which involves writing differential equations and seeing how stresses vary as strains as a differential in differential form. That was also shown by Sir for one of the cases, and it was shown that both tend to give similar values, but in more complex loading, theory of elasticity gives you the accurate solution. So, sir multiple times mentioned that you need to also correlate with experiments which are carefully done in order to show that your analysis is correct. Mhm. So, therefore, therefore, due to these stresses, if you have a unsymmetric cross section, something like this, this is the cross section, this is your beam, and you are loading it. If you have this kind of cross section, due to the shear stresses which are developed, this can undergo some rotation when you are loading it, and this is due to the shear stresses tau zx, tau xz, both are the same, which are developed. So that was all which was covered in week 9, especially in lectures 4 and 5. In lecture 6, covered some more uh, specific cases like composites, and he solved some numericals and showed how you can develop the develop the relations for composites and find out stresses and strains for particular questions. So the important thing that you need to keep in mind from this lecture is that in your beam cross section at the neutral plane, you will have tau xy, shear stress the highest, and the stress state will be 0 tau 0 in the 2D plane. Of course, in Z you will not have anything, and if you go near the top or the bottom surface, then you'll have sigma stress, axial stress as maximum, and you will have this kind of state, sigma 0 0 0, and the axial stress is there, no shear stress is present. That was all from week 9, lecture bending 4 and bending 5. I think now we can move to the questions, since mostly it's especially bending 5 and 6 are about numericals for composite materials and different kinds of loadings having different materials of different cross section areas. but we'll just look at some non-numerical MCQs. Archita will cover the more numerical ones in her session. Let's take a 5-minute break and then we'll continue. Hello. Let's continue. So we had gone through the key concepts which were covered by sir. Now we'll look at some questions which are related to those concepts. These are not from the current assignment, as I had told in the previous lecture also. We will not be covering the current assignment questions directly. If there are any doubts, you can post in the forum or ask here up to the deadline of the assignment. Then we'll help you with the current assignment. But for now, we'll only be solving the questions of the previous year assignments. So let's start with the questions. First question, for a beam subjected to 3-point bending, the value of shear stress at the top and bottommost fibers of the beam at a distance L by 3 from the simply supported end, if L is the length of the beam is. So we have 3-point bending here, but we can still simplify what is being asked in this problem. There will be certain shear stress and bending moment occurring at the point L by 3 mentioned here, in which we are interested. Hmm. But we know that tau xy, the shear stress acting on the x plane in the y direction, will mm, be parabolic, and it will be zero at the surface, that is at the top and bottom. So even though this will depend on the amount, the value of the bending moment which is being applied, mm, or the shear stress that is applied, still, since we know that it will be zero at the surface, you can say that the answer will be zero. Next question. The variation of shear stress over the depth of a beam away from the points of loading having a rectangular cross section is. So we have seen this also. The relationship is parabolic. Mm, the exact relationship you can check in sir's video lectures. It is somewhat proportional to, I think, h by 2 whole square minus y square. So at y equal to h by 2 is equal, it is 0. Um, yeah, at y equal to plus minus h by 2, tau equal to 0, and at y equal to 0, here y is being measured from the neutral plane. So on the neutral plane, tau is maximum, and the relationship is parabolic, since it is since you have the integral y dA by I term here. So if you simplify it, you will see that it is parabolic. Let's go to the next question. The stress tensor at a point P inside the cross section of a cantilever beam based on strength of material solution can be represented as. So P is inside the cross section, we have been told. So we have already told that at the top we have zero shear stress, in the middle we have highest, but in the middle, that is at the neutral plane, we have axial stress equal to zero, and in between we have both axial stress which varies linearly over y, and shear stress which varies parabolically over y. So the correct answer will be this: sigma y will be equal to 0 as per strength of material solution. Exact solution might have some value of sigma y also. Hmm. Also, we can see here that, so this is just I have included uh, image of photoelastic material, photoelastic beam, which is being loaded, photoelastic beam, which is loaded like a cantilever. So one end is fixed and the other end is loaded, and we are seeing the fringes which are occurring, which are isochromatic fringes. That means sigma 1 minus sigma 2. The difference in the principal stresses is being shown in these fringes, and we see that near the free end you have more higher concentration of fringes, while near the loading end you have very less stresses occurring. This is because the bending moment is highest at the free end and lowest at the loading end. So due to that, the axial stresses are also highest at the free end. That's why you have this kind of a situation. And we know that tau is proportional to V shear stress, which is constant over the whole of this. So tau will be constant over the whole of it. Also, since we have quite a lot of time right now, nobody has joined, so there are no doubts to discuss. Usually, earlier it used to take more than 2 hours to finish due to the multiple doubts that were there. But this time there aren't any. So I'll use this time to just look over the parabolic equation, which has come multiple times in the assignment also, how it was derived. So force equilibrium was done. Mhm. The difference in axial stresses on two directions was written down, and it was converted to moment because we know the value of moment. And since we are interested in dou f by dou x, we can do differential of moment to get the shear stress value, and then this will give you the shear stress value. Sorry, to get the, this is the shear force experience V, and when you divide Q by B, Q is your shear flow dF by dx. When you divide it, you get shear stress. It's something like this. That was the derivation for uh, shear stress. And here you can see that when you integrate y dA, it's y into b into dy, and this uh, will come out as y square by 2. At h by 2 you have it as maximum, it as 0, y equal to h by 2. So when you put the limits, you get this value. And let's also look at stresses in the tau at tau zx. So stresses in the z plane for open sections. Hmm. Mhm. So I was talking about closed and open sections. If you have a closed section, you have a movement, you have axial stresses like this. On the top, you have the tensile, let's say tensile, or in case of cantilevers, yes, tensile. At the bottom, you have compressive stresses. In this, it's at the top compressive, bottom tensile, and both of these are cancelling each other due to this neutral plane which is passing through. So for the closed section, the net axial stress in the x direction is 0. But in case of open section, you only have, for example, here stresses which are in the or which are in one direction, right? So there is no balance of forces occurring here. There might be some resultant force, and due to that, we have a shear stress acting to counter that. Mm. Yeah. So I think that explanation is enough. Now let's move back to our questions. Yeah. Next question is question 5. Identify the correct variation of shear stress tau xy along the depth of an I-beam as shown in the figure for the load applied in the y direction. Enter the corresponding alphabet as the answer. We know that tau equal to v into integral y dA by b into I think I z z. Hmm. Oh. From this, sir has already actually shown this, that if you have this kind of I beam, then at the top region, the area is much higher. Maybe I'll go to the concerned part in the book where he shows the diagram for explaining. Hmm. 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 So here sir has shown that in the plans you have this value VA1 Y1 by B1 into I is easy, and in the web you have this value. So we know that B1 is much higher than T, the thickness here at the web. So Mhm. So it's because of the width which is being encountered at the flange. It is B, and at the web it is T1. And because B is higher, tau xy will be lower at the flange, which you can see here. Okay, now we have seen this. Let's go to the next question. So the correct answer is A. You have parabolic with a jump here. The next question is the shear center of a beam is. So the reason we have a so what a shear center means is it's a point on the beam about which at which if you load you will a point with respect to a beam where if you load you will not have any bending taking place. So because if there is no bending, you say that that is the shear center of the beam. So if no twisting takes place, uh, there will it will be the shear center. So the correct answer is D. Next question. Mhm. This shows variation of different stress components over the depth of a beam having rectangular cross section. So what will be the variation for different stress components. First is sigma x. We know that sigma x varies linearly. It should be A. Sigma y. So we'll see this later. Next is correction to sigma x as per theory of elasticity solution. We'll see this also later. And next is tau xy over the depth of the beam. We have seen this, it's parabolic, so it's B. Now for these two, as per strength of material solution, the sigma x should have a variation of A and sigma y should have a variation, it should be 0. But if you consider the exact stresses occurring, then there will be some differences. Sir has already mentioned this in his previous lecture. I'll just open that part and there we'll see it in more detail what the distribution should be. Hmm, it should be in this portion. Hmm. So here sir has explained that if you consider theory of elasticity, then so earlier we idealized sigma y to be 0 for pure bending as well presence of stress. But sir has told that since you have some load occurring in the y direction, there has to also be some sigma y to maintain equilibrium. So some sigma y will be present. Give me a minute. So as I was saying, because we have loading in y direction, we should expect some value of sigma y, and it will be like this if you use theory of elasticity. And even sigma x will not be totally linear. The actual one will be something like this. So instead of being like this, it actually follows something which is like this in real life. So if we go back to our question, so this is because of second order effects, because we have shear stresses also, which we earlier were decoupling with the bending moment, but you cannot decouple it like that, uh, because those also have some effects. So that is why we have this kind of change. So the correct answer to question 9 will be C, to question 8 will be D. Coming to the last question, for which of the following cases plane sections remain plane before and after loading? For axial tension of a rod of hexagonal cross section, it should remain plane because you are having uniform elongation. Twisting of a shaft having a rectangular cross section, we have seen that if the cross section is rectangular, you have anticlastic kind of curvature. So some curvature forms. So this will not be true. Twisting of a shaft having the circular cross section. Here we have seen that the planes still remain planes. Bending of a cantilever beam of rectangular cross section with loading at the end. Here we have seen that it would have been plane, still a plane, but because of loading at the end, there is also shear force. And in that case, the assumption of plane remaining a plane does not is not true. It might become curved. So this is false. But here in the last option, you have pure bending, and there you this assumption will hold. It will still be part of the plane. We have seen in Sir's lectures. So option correct answer is A, C, and D and E. Yeah. With this, the questions are done. I hope these lectures are useful for you all. I'll upload this one by tonight to my YouTube playlist where you can view it. Let's wait for 5 to 10 minutes in case anyone joins us has any doubts. Else we'll finish it. So I'll just wait for 5 to 10 minutes more. Hello. So, since nobody has joined, I'll wrap up this session now. We have discussed on week 9 content. So, next week, Friday, 6 to 8 p.m., we'll do the problem solving session for week 10. I'll close now. Thank you.